So the process about which we have to talk today is the friction stir welding. Okay. So I'll be using both whiteboard as well as the PPT for explaining the different aspects related to the friction stir welding. This is comparatively new process. It has been, you can say, comparatively recently developed. Say it was developed in 1991 by the Welding Institute, UK. So this is commonly known as TWI. It's a UK primarily based on the this institute focuses on the various manufacturing aspects and the metal processing. Okay, so this lot of research interests has were there on this friction stir welding process because its capabilities, like ability to join the metals in different configurations, ability to join the different types of the metals like dissimilar metal joining, as well as the quite good welding speed and ease of the joining. So there were a number of positive sides related with this process, and that is why there has been a lot of efforts which have been made to develop and to characterize the joints for the variety of the applications and investigate various aspects. And later on, using this friction stir welding, so many variants have been developed. Say as per the need, or you can say to have the improved performance of the joints developed by using this solid state joining process. So just for to name a few, like there is a stationary shoulder friction stir welding. In normal or conventional friction stir welding, our shoulder rotates, but the one variant based on the friction stir welding is wherein the shoulder by and large remains stationary, or very small size shoulder is used in order to reduce the heat input, in order to reduce the various adverse effects which are produced by the large size shoulder. Okay, there is another variant like friction stir spot welding, so wherein you will see that just the two sheets are being joined like this in, say, lab joint configuration. Initially they are separate, and when the friction stir spot welding is performed, you will notice that the two have formed a kind of the joint like this. Okay, so that the top sheet is deformed and the nugget is formed, and the bottom sheet is subjected to the partial penetration deformation, and so the bottom sheet participates in joining, but the extent of participation is limited. So there are again multiple variants in the friction stir spot welding as well. There is one more variant that you can say that is known as thermal stir welding. This is nothing, just like say external heat assisted uh, friction stir welding. Okay, so these are some of the you can say the variants on which people are working, or the lot of things are going on uh, in order to like say to develop the, like say the different metal joining or dissimilar metal joining. That is one, for producing the different weld joint configurations, uh, which like say normally we develop the butt joint or the lap joint, but you may need a very unique kind of the joint configurations. So for that, like the plate joining is different from very thin sheet joining, or similarly your you can say the tube joining. So the different joint configurations using the friction stir welding or its variants need lot of efforts with regard to uh, the tool geometry, the welding parameters, or use of the external sources for developing the sound joint economically without compromising the capabilities of the joint. Third one is like uh, another area on which work is done during the friction stir welding is like joining of the high temperature metals. The process was initially developed for low temperature metals, like TWI initially developed the FSW for low temperature metals like aluminium, magnesium kind of thing, which are relatively soft, of a low yield strength and the good ductility. But when you talk of the high temperature metals like steel, titanium, cobalt, super alloys, they will be requiring much more the robust systems and more or much better control over the conditions that are needed, because you have to deform the metal uh, which are of the high yield strengths or very low ductility. So the kind of conditions that you need to deform the metal at, metals of the high yield strength, low ductility, you need to you need to come out with the further improved the setup, tooling, and the external sources of the energies in form of heat or some other kind of thing that can facilitate the deformation of such kind of the high temperature metals. That is why FSW of steel or titanium or cobalt or the super alloys, those are uh, FSW of such kind of the metals is considered to be difficult. So a lot of people do work or research is carried out in these areas. The another problem that requires lot of attention and efforts for research in the FSW is on the, like the limited limited tool life, since you are deforming the metal at comparatively low temperature, which might have not got softened sufficiently, or the metal when it is softened may interact with the tool metal itself. So we are anterior of the tool itself is a problem. Tool itself is a problem in your friction stir welding. So, so what is needed here is like you use the such kind of tool which sustains or which retains its geometry dimensions for long enough so that it can be used really for developing the joint of the greater weld lengths without need of the replacement. And the problem of the tool wear is more pronounced or severe especially when we are working with the high temperature metals. So for example, maybe die steel you can use for joining of the aluminum and magnesium, but for die steel, if you start using for welding steel or something else, you cannot weld actually. So what we do next, better alternative is use of the carbide tools, say tungsten carbide, and then it can weld maybe thin sheets, but very limited tool life will be there, maybe you can weld. So that is why further PCB and kind of the tools are used, which are very costly, and you need very special precautions for making those tools, which can sustain not just the high temperature but also the wear conditions which are imposed during the friction stir welding. So all these are the different variants of the friction stir welding, and these are the factors which are driving the research in this domain. Okay, so let us see how the joint is developed and what is the basic idea behind the friction stir welding. So here what we see, there are two things mainly in friction stir welding, or you can say the joint is developed primarily with the help of your friction stir welding tool. So the tool is the crucial thing here, apart from the plates to be joined. So the plates to be joined is something that you need in any case, and the firm holding of the tools, the workpiece. So the workpiece is held in its position very firmly. Okay, and this needs to be supported very firmly on the suitable robust table. Okay, like this. And then so you can say the workpiece holding firmly is very crucial. So you may need proper fixtures for this, so that the workpiece, the components to be joined can be held in its position without any motion or the movement during the welding, because your heavy forces will be acting during the joining. So in order to avoid any kind of, if there is a little shift in the plate positions, then the joint will not be formed, and you may find the weld line at somewhere else than where you need to develop a joint. So joint may not be developed at all in that case. So this is first thing, proper holding of the workpieces in position. And then what we need is very firm tool also, which just like any cutting tool, you need the properties of the tool material of such that it can retain its dimensions. Okay, so it means it must be wear resistant, and it retains its mechanical properties. Okay, so mechanical properties you have, like say hot hardness, it must retain its hardness, and it must be tough enough so that when it is plunged or when it is moved, it doesn't it doesn't get fractured. Then it should be chemically inert as well. Okay, so chemically inert because metal will be coming, the tool material will be coming in contact with the workpiece metal at a high temperature. So there will be very close metal to metal contact, and if there is some kind of the interaction, that too at a high temperature, say 400 to maybe 1000 degrees centigrade, depending upon the metal that you are welding. So the two metals, when they are interacting at a high temperature in direct metal to metal contact, when there is a relative motion as well, so this kind of interaction can lead to the formation of some kind of the compounds. Okay, and these compounds may get delaminate or get removed during the welding. So chipping of or removal of such kind of the layers which are being formed can lead to the very rapid wear of the tool. So the chemical inertness, especially to the workpiece, is workpiece metal is important. So the dimensional stability, tool material properties, and like say the chemical inertness, these are some of the kind of properties that you need. So let's say the tool which is held in a suitable tool holder, and that will be getting the power from the spindle of the power drive. Okay, a spindle of the machine, say FSW machine or vertical milling machine or anything of that sort that can use. So there has to be a delivery of power from the spindle on which the tool has been mounted. Okay, and this tool primarily has the two components. So the component one is this, that is shoulder. Okay, and another is this pin. This is the second component. So there are various names, like you can call it is a pin or probe also. Probe. Okay, so both contribute in the joining process or friction stir welding process. Okay, there are various configurations, dimensions, and geometrical aspects. So the diameter of the tool as a shoulder, let's say the D, and the diameter of the pin, let's say small d. A particular kind of the ratio is required to be maintained in order to develop the sufficient heat and to realize the desired deformation. So for developing the desired heat as well as to realize the desired deformation, a dy, capital Dy small d, that is that shoulder diameter to the pin diameter ratio, is maintained. That can vary, say from 2 to 3.5. Okay, usually it is on the, like say this is the kind of range. So maybe optimized one, depending upon the tool, metal, and workpiece combination, you can work with 2.5 to 3.5 kind of the ratios. So that is one aspect. Second aspect is about the tool pin length. Okay, so tool pin length is kept around like say 0.2 to 0.5 mm less than the thickness of sheet which is to be welded. Let's say the thickness of sheet to be joined is say 5 mm. So the tool pin length will be keeping around say 4.6 to 4.8 mm kind of thing. So that the tool pin penetrates enough, deep enough into the plates which are to be joined like this, and so that there is no direct contact between the anvil or the supporting base metal, and enough heat is generated in order to cause the softening as well as the deformation of the metal below the tool pin, so that the through thickness penetration is realized and the joint is developed accordingly. Okay, so that is about the tool shoulder and the tool pin. Okay, then the next aspect here is like how does it work. So here say you have got the tool shoulder and this is the tool pin. Okay, so the different aspects that contribute in the process of the joining, that involves in FSW is like this. Like say the two components to be joined will be placed firmly in abutting position like this, touching to each other without any gap, and they are held firmly. Yeah, okay. And then your this tool, okay, the tool is first rotated. So the rotating tool is first brought in contact with the surface of the workpiece. So obviously the tool pin, lower surface of the tool pin will be contacting the surface of the workpiece, and then it will be plunged gradually. Okay, so this is first lowering down the rotating tool or moving up the workpiece, so that the tool is plunged, rotating tool is plunged into the workpiece gradually. This has to be done very gradually, because the metal is hard, it is at a lower temperature, so it will not allow the penetration so fast. So the plunging must be done very gradually. Okay, so that whatever heat is being generated by the lower or bottom side of the pin, that will keep on softening the metal due to the frictional heat. Okay, and so the temperature of the base metal will gradually keep on increasing. That is one. Once the whole of the pin has been, say, penetrated, so in that situation your shoulder should come in contact with the surface of the workpiece. Okay, so let's say this is the position when the tool has been completely plunged to the desired depth. So in that case there will be three zones that will be producing the heat due to the friction as well as deformation. So here what we'll say, the one zone that will be contributing is this one, that is the tool pin, the bottom portion. Okay, then this vertical surface of the tool pin, the vertical surface that will be producing, and then the shoulder, the portion which is in contact with the shoulder. So the shoulder which is in contact with the workpiece, that will also be generating the frictional heat. Okay, so all these heats need to be taken care of or need to be considered while looking into the various aspects related with the friction stir welding. So heat is coming from the heat being generated by the shoulder. Okay, then heat being generated by the tool pin. Okay, so the tool pin has got the two components. One is the surface of the pin, you can say the pin surface, plus the bottom of the pin, bottom of the pin. So the tool pin is contributing towards the heat generation from the two aspects. One is the bottom of the pin and another is a vertical surface, and the third this is about the tool pin and this is about the shoulder. In both the cases, if you see the tool pin is this one. So if you see the dimension wise, if the tool pin is very small, then the surface area will be less. You can say pi by 4 d square into L. That will be giving you pi d L. This will be giving you the complete volume. And if we are interested in the just surface area, maybe we can write like pi d into L. Okay. On the other hand, the bottom surface area of the pin, so this will be pi by 4 d square. So if you see, so here is small d because we are talking about the tool pin. So if you see here, the heat being generated by the vertical surface of the pin or the bottom surface of the pin, both are the function of the pin diameter and its length. Okay, so here the tool pin diameter, okay, pin diameter and the pin length both will be contributing towards the heat generation. Okay, so larger the diameter, greater the length, both will be increasing the heat generation. And the same is true for the shoulder diameter. So when your shoulder is of the, like say the shoulder is of the smaller diameter, so shoulder, say this is the pin and this is the shoulder diameter is large, then the greater will be the area which will be rubbed, greater will be the area of the workpiece that will be rubbed by the shoulder. So basically if you see here, so the shoulder, okay, so whether the shoulder is of the larger area or a smaller area, so here in between you'll have a pin. Okay, so if the diameter, and this is the workpiece, one side and another side, right? So this is the area that will be under the effect of the shoulder. Larger the shoulder diameter, greater will be the frictional or deformational heat that will be produced. So increasing the diameter of pin, increasing the diameter of the shoulder, both will be increasing the heat being generated. Okay, so apart from these two aspects, like the tool shoulder and the tool pin dimensions, okay, what are the other aspects, like at what speed the tool is being rotated? This is one that you can say, the rotational speed. So simple, it is very simple, like at a particular location, if you keep on rubbing the tool at a much faster speed, the more frictional heat, more localization, more rise in temperature will be taking place. So let's say this is the weld line in top view, and this is the tool pin, and this is the shoulder the tool dimensions, or you can say shoulder dimension. So if you keep on rubbing at a particular location at say 200 rpm or 800 rpm, so obviously when you rotate at a much higher speed, the more frictional heat generation in less time will be leading to the more localized rise in temperature, and so the increased temperature will be causing the more thermal softening. So when you work with the greater rotational speed, so this will be simply increasing the both the friction and the deformational heat that will be generated, and that in turn will be increasing the temperature of the metal. Similarly, when you move the tool at low speed or at high speed, that is a different thing. On these things I will come little later, on the different aspects of the welding parameters. So let us talk about like the sequential steps which are used in friction stir welding. So there are let's say the three steps main. The first is the tool plunging, then tool dwelling at a particular location, and then tool traversing, and you can say the tool withdrawal from the workpiece. So for regarding the plunging, I have already said, like between the workpiece you have to plunge the tool pin gradually until the tool shoulder starts touching to the surface. Okay, and little deeper plunging is done, so that there is enough normal load, okay, for facilitating the forging or consolidation of the metal which is being deformed. So consolidation or forging action is facilitated by this normal load, which is ensured through little deeper penetration of the shoulder below the surface of the workpiece. This may be very small in magnitude, maybe zero point 0.1, zero point 0.2, 0.3, like that, depending upon the kind of metal which is being joined. Okay, so that will be dictating the normal load, basically the depth up to which the tool shoulder is getting plunged into the workpiece, while the tool pin is plunged completely in at the weld line, so that it generates the heat enough for. So once the tool pin has been plunged completely, we make another diagram. Okay. So once the tool pin has been plunged completely at the weld line, and so it will keep on generating the heat. This is a shoulder. So the shoulder and the pin. So what we do basically, the uh, after the plunging is over, okay, we keep on rotating the tool at a particular location for some time, maybe depends on 5 to 10 or 15 seconds, depending upon the kind of the thickness or the metal that you needs to be welded, so that there is enough heat generation for achieving the desired rise in temperature of the metal all around the tool where it is rotating. So the rise in temperature will be causing the thermal softening, which in turn will be reducing the yield strength and increasing the ductility. These are the prerequisite things. Once it is done, then the rotating tool there. So after the dwelling of some time, what we do, we try to start giving some kind of the motion to the tool. And how it is done, let's say this is the weld line, your pin and the shoulder were dwelling here for some time, and once you achieve the desired temperature rise, you start moving the tool, because tool in FSW basically remains fixed and workpiece is given movement, so that the desired relative movement between the tool and workpiece can be realized for developing the joint. Okay, so this tool pin now will start so this because of this tool, you can say the rotation as well as the heat generation and the deformation, you will notice. Let's say the tool is rotating this way and this is the welding direction. Okay, so the side which is matching, if the side of the workpiece having the rotational direction of the tool and the welding direction same, say in this case, if this is the tool which is rotated like this in clockwise direction and this is the welding direction, then this forms the advancing side, and the other side wherein the rotating direction and which is opposite to that of for which the welding direction and the rotational direction are opposite, that is termed as the retreating side. Okay, so here in general it is a very established thing that the advancing side generates the more frictional as well as the deformational heat as compared to the retreating side. So the higher heat and higher temperature generation in the advancing side, and the lesser heat and the lesser rise in temperature occurs on the retreating side. So the low heat and lower temperature on the retreating side. Okay, so if we are working with the high dissimilar metal combinations, so we will be putting the advancing side high temperature metal, and on the retreating side we will be putting the low temperature metal, so that at least some kind of the softening can be realized by putting the high temperature metal on the advancing side. Okay, so sufficient heat has been generated, then what will be doing, moving the workpiece. Okay, so that the entire and in this process of the joining, what will be happening, let's say this is the tool and this is the shoulder, and this is the weld line, right, along which the joint will be made. So the welding direction is this one. Whenever the welding is happening, you'll see the advancing side will be experiencing the greater heat generation as compared to the retreating side. So for this tool direction and this welding direction, what you will notice that the advancing side and this is the retreating side, so there will be the greater softening of the metal in the advancing side. So what will that metal will be moving from advancing side to the retreating side, and then some of the metal will be moving from retreating side to the advancing side. So what is happening, basically the metal is being brought from the front side to the back side like this. Because here on the advancing side there will be greater metal softening as compared to the retreating side. So metal is so not just thermal softening, but the deformation is coupled with the transport or movement of the metals from advancing side to the retreating side, or from the front side to the back side like this. Okay, and this in turn results in the metallurgical continuity. If we see this section, then what we will notice, like the joint is being made like this, and here the metal is being moved in this manner, and in the top view if you see, the metal is being moved from the front side to the back side, and then back side to the front side like this. So in order to develop the metallic continuity all along the weld line, you have to move the workpiece through the tool at a particular speed, so that the entire the joint length is covered, and the joint is made all along the weld line which is to be joined. Okay, now say you are generating heat at a particular rate, which is coming from, say, the friction as well as deformation coming from the both pin and shoulder, and you are moving the workpiece at a set particular speed with respect to the given position of the tool pin. So there is a welding speed that you can say at a particular, so you can say the particular kilojoule, that is the heat which is being generated in unit time, and the welding speed which is being given. So if we can easily find the kind of the heat being delivered to a particular line, a particular location for a given welding speed. So the net heat input in kilojoule per mm can be identified from the frictional deformational speed and the traverse speed, or the speed at which there is a the workpiece is moved with respect to the tool. Okay, so in general here we'll say, if your tool rotation is high, certainly your the heat generation rate is high. Okay, heat generation rate is high. Okay, so that will simply, for a given traverse speed, increasing the rotational speed will simply be increasing the rise in temperature or increasing the net heat input which is being given. Similarly, when the tool traverse speed, or you can say the workpiece traverse speed, is increased, so for a given RPM, if you are moving the tool at a very fast rate, means for giving heat generation rate, if you are moving the tool at a higher speed, then certainly the value of the net heat input, that's kilojoule per mm, will be reducing. Let's say, just for an example I'll give, you are giving the heat say 20 kilojoule per mm, 20 kilojoule. Okay, that's the rate of heat generation, and you are moving the weld joint at a speed of, say, no, say 2 or say 20 mm per second. Okay, so in that case our net heat input will be 1 kilojoule per mm kind of thing. So this is 20 mm per second, and here 20 kilojoule is the rate at which heat is being generated. So we'll be having the 1 kilojoule per mm kind of thing heat input. And if the welding speed or the traverse speed is increased to 40, so for the same rate of the heat generation, using the 40 mm per second will be leading to the 0.5 kilojoule per mm kind of the net heat input. So increasing the tool traverse speed, basically reducing the net heat which is being supplied, and that in turn will be reducing the temperature which is being delivered. And reduced temperature may lead to the reduced softening of the metal. And reduced softening means your yield strength will be high and the percentage elongation will be less, and this situation may lead to the formation of the defect or limited metal flow or limited metallurgical bonding between the two. So the defective joint can be formed. So you need a very good combination of the tool rotational and traverse speed for developing a sound joint. So in general, simple thing is tool rotational speed is one that will be dictating the heat generation significantly, and increasing the tool rotational speed will be increasing the rate of heat generation. Similarly, the tool traverse speed or the welding speed will be dictating the net heat input which is being delivered, or which can be delivered after proper adjustment of the traverse speed. In FSW, basically it is about the heat generation and the deformation. These are the two things. So I was telling, like, this is the tool. Okay, the tool is rotated, a rotating tool which is having one shoulder here. So this is the shoulder, and in between you have one pin like this, right? So the rotating tool, this is what you can say, the welding tool, shoulder and pin. Okay, now there are various configurations about the shoulder, or the pin as well. It can be cylindrical like this, or it can be tapered, it can be threaded. There are various possibilities as far as the tool pin geometries are concerned. So basically this tool pin and the shoulder, these two contribute significantly in the process of joining. Okay, so when the so if you see, as I said, these are the two components which are to be joined, and along the weld line, initially the tool will be plunged, it will be dwelled, or it will be rotated at particular speed. Once you achieve the sufficient temperature, then movement is given to the tool or to the workpiece, so that the relative motion is realized and the joint is formed all along the weld line. So if you see, this is the welding direction, okay, and this is the tool rotational speed. So the welding direction and the tool rotational speed, the side in which both are same, that is the advancing side, the welding direction and the rotational speed. If these are same, the side in which both are same, that is called advancing side, and the welding direction and rotational, these are the two speed direction of rotation, these two are opposite, so that will be the side will be termed as retreating side. Now you see further the kind of the deformation and the heat generation which will be occurring, and the way by which it is transferred. So like say this is the tool, and its movement along the weld line will be giving us the weld joint, not the tool, but basically the workpiece is moved. Then the tool rotation, this is the tool rotation, and this is the shoulder which is coming in contact with the workpiece, so generating the frictional as well as deformation heat. And this is the section where tool pin is in contact with the workpiece. Okay, this section. And you will see since there is a continuous frictional heat generation, deformation, movement of the material, so you will always see that there is, so this is the zone of the metal that will be experiencing the heat as well as the deformation, and that in turn will be leading to the generation development of the weld joint. So you see, this is the kind of the movement that will be happening all around the tool. Okay, so the material is getting deformed. So this is the primary heat generation source is about the friction only, and the deformation is basically the secondary heat generation source. Okay, you know that if you just keep on bending a particular sheet or wire, it becomes hot just like that. So here also, like say your the heat being generated due to the constant rubbing of the tool and the shoulder, tool pin and shoulder with the workpiece of the components to be joined, so that will be generating the frictional heat. And in this process your metal is also getting deformed, so that will also be generating the secondary heat. So you can say the primary heats or secondary heat sources are, because so the primary is about the friction and the secondary heat is about the deformational heat. Okay, so this is about that. This shows like effect of the tool pin and the tool shoulder diameter. So if we take up say the different types of the tool like this, okay, of the different sizes, then what you will notice, it will be affecting the frictional area over which the frictional heat is being generated, and that is affected by both the frictional the tool pin diameter and the shoulder diameter. So you can say there are empirical relations have been developed to check the kind of the frictional heat generation or the by the shoulder frictional heat generation from the bottom of the tool pin, and the frictional heat generation from the surfaces of the vertical surface of the pin or the tapered surface of the pin as per the case. In general, in all these cases, what you notice, the primary factors that will be governing the heat generation is like heat generation is proportional to the heat generation, the shoulder diameter. Okay, that is one thing. So because the shoulder diameter is usually significantly greater than the pin diameter and the pin bottom diameter especially. So so here so these are the various kind of the assumptions which are say, so the maximum heat generation occurs when you work with the larger tool diameter, and the heat generation due to the friction in tool 3 is around 14% to that of this. So actually this was work done by one of our students. So here I just want to show you using this schematic like how the procedurally we are proceeding during the friction stir welding. So say this is the rotating tool which is so tool and its position by and large remains fixed, only the workpiece is moved up so that you can achieve the desired plunging. So against the rotating tool, basically the workpiece is moved up, and then gradually the plunging is realized. So when this plunging is happening, this has to be very slow, otherwise what will happen, your tool may break due to the limited toughness. And because these tools mostly hard, so they may have the limited toughness as well. So the plunging has to be gradual so that there is enough rise in temperature of the work pieces. Okay, once the rise in temperature has been enough, we'll continue to rotate the tool at a particular location. That's what you can say that they're dwelling, and we'll be waiting for a rise in temperature to the sufficiently high level so that the thermal softening is realized, and thereafter we start moving. Say if earlier if we were here, now we'll keep on moving the for a given position of the tool, we'll move the workpiece so that the entire weld line is covered. Okay, that is the case of your the butt joint. In case of the lap joint, say use this is just an example of the dissimilar metal joining, but what we can do here, the two plates are kept like this in lap overlap position, and then tool is plunged from the top position, and then it will be penetrated to a certain distance. No, this has to be an optimum, not very less and not very deep, because in both the cases our joint performance is very badly compromised. Limited strength, limited penetration will be leading to the you can say the interfacial fracture, or if the penetration is too deep, say if it is up to here, then it will be leading to the failure from the base metal itself. And this is the kind of the geometry that is developed after making a lap joint. Okay, and these are the different factors that will be governing the kind of the joint properties. Okay, so here although there is a continuous metallurgical continuity, but the length in these cases is governed by the kind of this interface. Now if you compare this the friction welding with the fusion welding, so in case of the fusion welding, what we have, just for sake of comparison, in fusion welding we supply lot of heat. As a result of that, we have very large size weld, very wide heat affected zone, so that will be leading to the significant softening of the metal due to the reversion and grain growth, especially in precipitation hardenable metals. But when we take up the friction stir welding, which is comparatively low heat process, so that will be leading to the reduced weld nugget size and the reduced heat affected zone, so the damage is somewhat reduced. There is one more variant where we don't rotate the shoulder, we just rotate the pin only. As I have explained so far, like the pin shoulder contributes significantly in heat generation because of the large diameter, but the newer variants which have been developed, that includes the stationary shoulder. So in case of the stationary shoulder FSW, heat generation is further reduced, and that in turn will be reducing the nugget size as well as the heat affected zone which is being formed on both the sides.